morning, good afternoon, good evening. Welcome back to Chapter 3. We're talking about the biologically important molecule. We've talked about carbohydrates and lipids. We're currently talking about proteins. Remember that proteins are made of amino acids. Amino acids are building blocks for proteins, and there's 20 naturally occurring amino acids. The way you link together amino acids is by what's called a peptide bond. It's still a dehydration synthesis. We talked about this at the beginning of the chapter. I link together amino acids to make polypeptides. Remember, we just said a second ago that when you link together amino acids, it's referred to as a peptide bond. I'll show you a picture in just a minute. It's called a peptide bond. If I link together several amino acids, it's called a polypeptide. Many peptide bonds are used to link together many amino acids. It's not complicated enough to be a protein until it's at least 50 amino acids long. When you are looking at the PowerPoints, anywhere you see AA, it will always stand for amino acid. So here we have two separate amino acids that we're going to link together by a peptide bond. There is my OH group and my H group. Remember, I have to make water. I'm going to cut this hydrogen off of this amine group. I'm going to cut this OH group off of my acid. Where these two were, I'm going to make a bond between that carbon and that nitrogen. What do I do with those two? I make water. So those two get removed to make water. There's now an open bond on this carbon and this nitrogen. And so I'm going to make a bond between those two. And that bond between the two amino acids is called the peptide bond. If we look over here, there's that carbon right there. There's that nitrogen right there. And the bond between them is this bond right here, called the peptide bond. If I can do this with 2, I can do this with 100 or with 1,000. It says this is a dipeptide because it's 2 amino acids. A polypeptide is many amino acids. Once I get at least 50 amino acids long, then I have something complicated enough now to be called a protein. It's kind of like a single stick isn't really a tool. I got to add a bunch more pieces to it to turn it into a hammer to make it useful. Just 1 or 2 or 20 amino acids is not enough. It's not complicated enough. It's not big enough to be called a protein. It has to be at least 50. So, proteins, as you can imagine, tools have very specific shapes. A saw has a special shape. A hammer, a wrench, a screwdriver has a very specific shape that it has to be in to work. You've got to follow a very special set of instructions to make a proper tool, to make a tool that works. Amino acids are what are used to build proteins. I have to put them together in just the right way to get just the right protein. So as you can imagine, that if at least 50 amino acids makes a protein, that means a protein's a pretty darn complicated molecule, pretty darn big. They are really darn big. The average protein is 300 to 500 amino acids long. Some of them are more like 1,000 amino acids long. Really big, really complex molecules. The first step in making a proper tool, the first level of protein structure, is the amino acid sequence. Each amino acid that is used to build a protein has a specific place it has to go. Just like when you write a word, each letter has a specific spot it has to go in to make the right word. So these are my amino acids, these little purple pearls that we see. Each one represents a separate amino acid. This is showing you how an amino acid is constructed. There's the amine portion, my little central carbon, that R group, that again is different for each amino acid. There's that peptide bond right there between this carbon and this nitrogen group. This is my second amino acid. There's its R group at the top. And now here is my next peptide bond. Here's my third amino acid, the R group at the bottom. If I can link together 2 or 3 of these, I can link together a whole bunch of them. Just like you've got to put the letters together in the right order to get the right word, I've got to put the amino acids together in the right order to get the right word. And just like you can use the same letters more than once in a word, you can use the same amino acid more than once in any one protein. And to be fair, if there's only 20 amino acids, and it takes at least 50 of them in a row to make a protein, I had to use some of them more than once. You're going to use all of them more than once when you make a protein. Our first level of protein structure is the amino acid sequence. Only if you get the amino acids lined up in the right order to begin with can we move on to the second level of protein structure. And that second level is called secondary. The secondary level of protein structure is either the alpha helix, which is just a corkscrew, or the beta pleated sheet, which is a bit more complicated. The beta pleated sheet is very much like that fan that you made at that wedding that you went to in July. You took the program, right, and you folded the program back and forth to make a fan. That's the essential, that's the basic structure of the beta pleated sheet. Okay? So the alpha helix is a corkscrew, and we see it right here in this picture. The amino acids have been strung together in a corkscrew, and this is the beta pleated sheet right here. It's folds. So it's either curves or angles. Hard angles, soft curves. And so what happens after you string together the amino acids in the right order? So kind of imagine, I'm going to take a very long piece of string, and I'm going to tie it to a wall. I'm going to tie it to a doorknob. And then I'm going to put on the amino acids in the right order, one at a time. So I've got 200, 400 of these pearls, these amino acids, that are all strung together in the right order. And as long as I hold on to it nice and tight, it's going to be a nice straight line. But as soon as I let go, its parts of my string of pearls is going to twist into a corkscrew, while other parts fold into the sheet. And what determines whether it twists or folds? Well, it determines which amino acids are there. If the right amino acids are here, so they can link together like this, then they form the corkscrew. But if the right amino acids are here, they'll link together and form the sheet. So it depends on which amino acids are placed in which sections, in which places, which will determine whether it can twist or whether it folds. And this twisting and folding, if you can imagine, is that going to make a straight line, or is that going to make a kind of complicated structure? The twists and the folds are going to make a very complicated structure. It's not going to be a nice straight line of pearls like I had linked together. It's going to kind of twist into what appears initially to be a complicated, unorganized mess. It is not actually unorganized. It is highly organized. It is specifically organized to twist this molecule into the right shape so it can now do its job, so it can be a catalyst, so that it can make some reaction happen that would not ordinarily happen. It has to be the proper tool. I've got to, one, put the amino acids together in the right order. And when I do, parts of it will twist into the alpha helix, the corkscrew, while other parts of my string will fold into the beta pleated sheet. Once I have strung my amino acids together in the right order so it twists and folds in the right place, it'll twist and fold in the right place. And I know that this is difficult to see in this image. Please look at it on your own PowerPoints. But we can see how one section right here has been twisted into the corkscrew, and other sections have been folded into the sheet. If I've got twists and folds, it's not going to be a nice straight line. Every single tool has a special shape it has to be in to work. What if I went and I bent the jaws of the pliers apart? I changed its shape. Will my pliers work now? No, my pliers will not work because I changed the shape of them. The jaws can't touch anymore, and if the jaws can't touch, then it's useless. What if I take a saw and I bend it in half? Now my saw has a 90-degree angle. Is my saw going to work? No, the saw is not going to work because I changed its shape. A protein is a tool that has to be in a very special shape to work. And the way I get to that very special shape is making sure that I put the amino acids together in the right order so it twists and folds in the right places, so it twists and folds in the right places. This is called tertiary structure, primary, secondary, tertiary. This is called tertiary structure. Tertiary is called the functional conformation. Conformation as in conform, as in like the right shape. Functional conformation. The shape it has to be in to work. The functional conformation. The way you break a protein is by exposing it to heat, exposing it to extremes in pH, acid or base. If I do that, I can destroy the protein by making it change its shape. I've now bent my saw in half. I've now pried the jaws of my pliers apart. That's called denature. If you have denatured a protein or an enzyme, you have changed its shape and you've made it so it no longer functions because it is the wrong shape. Every single protein has these first three levels of structure I've just described. Some proteins have an additional fourth layer.